Hello and welcome to the iRevise Supplementary Series for A-Level Physics. This video is a bit of a continuation of the astrophysics. It's a bit of a hodgepodge. I want to talk about gravitational fields, orbits, Kepler's laws, escape velocity, projectile motion. We'll also take a look at electric and gravitational potential. That's the bulk of what I want to do in this video, linking all of these calculations I was just talking about to gravitational potential. We'll look at equipotential lines. We will skip past parts of questions which deal with the universal law of gravitation or Coulomb's law, anything with circular motion, calculating periods and orbits and stuff, unless it's a little bit more intricate, maybe a little more interesting, and questions which can help drive some important points home. This video is part 2 of 2. Okay, let's get on with things. Okay, and I've got a paper 3 from the Cambridge Pre-U 2016. Calculate the orbital period of the geostationary satellite. Well, we know it's 24 hours. That's 86,400 seconds. Boom. That's something I would hope know by now. Okay, 24 times 3,600. Geostationary satellite remains above the Earth, the same point on Earth. Explain why it must orbit the Earth west to east directly above the equator. Here's the equator. We're looking at it. Okay. If the sun's over here, we know the sun rises in the east. Here's the shadow. Okay, here's the shadow. Sun rises in the east, sets in the west. So when they talk about going west to east, I look at that as it's rotating anti-clockwise. I don't know why they would say west to east. Seems a bit confusing to me. So explain why it must orbit west to east directly above the equator. Well, if our satellite is going to stay above a certain location on Earth, and that's the direction the Earth rotates, then the satellite has to stay with it. I mean, I'm not sure what else they're looking for here for 2 marks. This is a bit of a tricky one. Let's see what they say. Because Earth rotates west to east, I would have said anti-clockwise, but there we go, that's fine. If it is not over the equator, it would move north to south to north. I'm not sure what they're trying to say. The satellite would rotate this way. I'm not sure why they're saying that. All right, so I'm not sure what's going on, what they mean by that, if that's necessarily true. But let's move on. Okay, so the radius of orbit of the geostationary satellite is this. Gravitational potential is given by that equation. Gravitational potential energy, yes. Calculate the gravitational potential energy of the satellite. We're just plugging in the mass from up above, mass of the Earth, and the radius they've given us, yeah? Calculate the kinetic energy of the satellite. Again, half mv squared. That's all that is. Okay, but where do you get the velocity from? You know the velocity is equal to the circumference traveled in a certain time period. They've given us the period. We set it at the beginning. You plug it in and get your answer. Comment on the relationship between the values. I'm not going to waste time on the calculation. Let's see what they say in the mark scheme, okay? These are simple plug-in questions here. So negative 9 times 10 to the 8 joules, okay? So 900 million joules in an energy debt. That's going to be your speed. You plug that in there and you get 4.5 times 10 to the 8. And the numerical value of the potential energy is twice of the kinetic energy, and it has a negative sign. So it's just something you would have come up with from calculating those answers. All right, the real interesting part of the question that I want to address here is values calculated in CI and CII apply to stable circular orbits. Put your values into the table. That's for a stationary circular orbit. So the total energy is negative 4.5. Okay. If you were to subtract 2.25 from negative 2.25, you'd have negative 4.5. It's going to be one of these subtracted from the total to get the other. Okay. Right, what happens with this bit? Now, from infinity, what would we expect the gravitational potential energy to be? It's gone up to 0, hasn't it? And we've also just gotten enough speed to escape this, and so we would have 0 kinetic energy just at infinity away, and so that would be a 0, okay? And for the 10R, how are they expecting us to calculate this? There must be an easy way to do this. Well, let's see. Gravitational potential energy is gm over r. So if we were over 10r, it'd be 10 times smaller. So would you agree 0.9? I think it stands to reason from the rest of our pattern here that the total energy would be 0.45 and the kinetic energy would be also 0.45. I'm going to subtract that from here to get the negative 0.9. How does that sound? Moving on, a probe could be launched to geostationary orbit with additional kinetic energy. Why would such a probe not be very effective for a journey to Mars, even if plotting the correct direction? Well, look at that number there is the same as this number here. That 95 kilograms was mentioned at the beginning of the question. So even if we had just enough energy to get away out of the pole of Earth, I don't think we're going to have enough energy to make it even on the way into Mars. That's just enough energy to overcome the Earth's gravitational pull. We're not taking into account the sun or anything else. Okay, you'd have to time it probably for when Mars and Earth are at their closest approach, but it's still not going to be having enough energy. I'm wondering what they say about that. They say it would be traveling slowly. It probably would once it's gotten to the infinity point from Earth's pole, the theoretical point. It would take too long to get to Mars, or it would stop before it gets there. It would need to take extra potential energy to get further from the sun. Well, that's what I was saying. We haven't taken into account the pole of the sun, have we? Okay. Or at Mars, its kinetic energy is 0. Yeah, it wouldn't have enough to get into an orbit, maybe. So, yeah, something along those lines. Let's get back to, let's see here. So, second row correct, top row correct, third row as a tenth of top row, fourth all 0. Good. So, I think we've got that. This is what we had. Okay. So, these add up to give us this. These subtract to give us this, and this is 1/10. Okay. Okay, same paper. Electric field is an area where a charge experiences a force. Let's move on. Show that the electric field strength at a point in a uniform electric field is equal to the size of the potential gradient at that point.
Oh, déjà vu.
Okay. Electric field strength is equal to force per unit charge. Force is equal to charge times electric field strength. This is what I call electric weight. It's analogous to the force of gravity. Field strength acting on the mass. This is electric field strength acting on the charge. So electric weight, what else do we want to say here? Well, we know that the potential is electric energy per unit charge. Or if you don't like that notation, we can say work per unit charge. We know the work is a force acting through a distance. And that force is QE, so QER over Q. We've got that the potential gradient is equal to electric field strength times a certain distance. So show that the electric field strength at a certain point is equal to the potential gradient at that distance, I suppose. Is that what they're looking for? The force on the charge in the field is here. Work done is charge times that force times the distance. Work done per unit charge. So you take that EQ, equals ED. So E equals the potential difference. E equals the potential difference. Not potential difference. Potential gradient. They've got here potential difference. The electric field doesn't equal the potential difference. Potential difference is the work done per unit charge. You cancel out the Q's. But E is not energy here, and E is not work. E is electric field strength. The electric field strength does not equal the potential difference. The electric field strength equals the potential gradient. Bit of a sore point for me there. I think there's a bit of a problem with the mark scheme. That should be potential gradient.
Dick, I'm very disappointed.
I'm sure it's only a glitch. A temporary setback.
You call this a glitch?
Okay, so here we've got a positively charged sphere surrounded by Earth sheet metal. And they're going to illustrate the shape of the field within and beyond the shield by drawing field lines from the sphere to the shield and in space beyond the open end. We start by just doing our good old symmetrical lines. Okay, so this is this sheet metal at zero potential. This is an equipotential line. Okay, and it's a little bit more on this side than you know between here. But what we'll have, we should have these lines coming out. But where are they going to continue to? Because we would want equipotential surfaces. I think this will come out and kind of go like this. This will come out and go like that. If you were to draw lines perpendicular to these field lines, we should get a region of equipotential as well. But let's not worry about that. But that's just to help guide you in how you would draw. How would you go about drawing these field lines? Okay. Right, and I think we would have one coming out here, and it might just head out this way. This one might just head out like that. Let's see what they say. So 2 vertical and 1 horizontal to the left, did that. At least 2 other lines meeting the cylinder at right angles, which we've done. Yeah, maybe I've not done it as clearly as I would have liked. But I would have had it coming out and hitting there, and this would have curved that way. Okay. So I'd say we've done that. At least 3 lines spreading out through the open end and diverging. We've done that, and it's symmetrical. So I'd say 4 for that one. Okay, and electric potential on the metal sphere is V. Draw 3 labeled equipotential lines. Aha, here we go. Okay. Showing these values 1/4, 1/2, and 3/4. So 1/4, 1/2, and 3/4. Just to remind, they've really given you a small diagram to do this, haven't they? All right. Well, let's get on with the equipotentials. So if I'm going halfway this distance, you know, and out here. This distance is gonna stretch, isn't it? It's gonna be a little further out, I imagine. And then here, I'm not sure, but this will be further out. It's gonna take a lot longer to get down to 0. It's gonna be stretched, I would imagine. So. And then you need to do, that's the 1/4, and then the 3/4 is going to be between the half and the final bit, won't it? Yeah, I'd say something like that. They say lines egg-shaped and at right angles to the field lines, so we've done that. And the position's correct and labeled. Okay, so I didn't go out and label these. I don't know if you connect these lines and say, hey, that's the 3/4. You can see they're egg-shaped, but that's a general idea. If this plate here is 0, the 0 potential is going to be much further out, and so we should expect sort of these egg shapes. That's the. Okay, so it'll be slightly longer out towards the open end is what they're getting at with these egg shapes. Maybe this one here I didn't show it as well. Maybe this could be stretched out a bit. It should go like that, yeah? Okay, so you have an idea. Right, on to section C of the same paper. We've got a problem here about the moon.
Hey, we've got a problem here.
This is Houston. Say again, please.
Houston, we have a problem.
All right, so the moon's orbital radius is 60 times that of the Earth's radius. The gravitational acceleration due to Earth is this. Calculate the acceleration due to Earth's gravity at the moon's orbit. Okay, well, acceleration due to gravity. Gm over r squared. Let's rearrange, and I'm going to say g1r1 squared is equal to G2 R2 squared. We'll let the GMs be the constants. Okay? Now, if we want to figure out, let's let the moon be 2. We want to find the acceleration due to the Earth's gravity of the moon's orbit. Let's make that G2. It's going to be equal to G1 times a ratio of R1 squared over R2 squared. Now, what is R2 squared? What is R2 squared? It is 60 times, right? So I'll have an R1 squared on top, and on the bottom I'll have 60 R1 all squared, won't I? For my R2 squared, it'll be 60 times R1 all squared. So in other words, these R1s are going to cancel out. And in other words, I'm going to have 9.8. It looks to me like divided by 3,600, which gives me 2.72 times 10 to the power of -3 meters per second. Look, for me, I think if you know you've got a formula and you don't want to mess around with these other constants, they didn't give you that m, for example, swing the r up squared up top, set it to constant, and then you just got like a before after kind of thing, like a Boyle's law. P1 V1 equals P2 V2. In this case, G1 R1 squared equals G2 R2 squared. Okay, watch your notation there. But yeah, that's very straightforward way to do that question. At the mark scheme, you were asked to do that calculation. Just the simple formula of what they had done up above. You just plug in the values they give you in the question, and you get that answer. And it looks to me, actually, since we were meant to compare, we didn't say this just a moment ago, but here we go. We're supposed to compare. It is the same value, isn't that 2.7 times 10 to the -3? Okay, and we've already explained how we got that. Again, pause the screen if you want to see words of wisdom from the examiner and the mark scheme people. Okay, and I've got a question here from Edexcel 2018, the paper 1, Core Physics 1. It's a projectile motion question. We're going 50 away. The time is 2 seconds. Calculate the angle. Okay, calculate this angle here to the horizontal. Let's break this up into components, x and y. All right, given that there is no change in vertical displacement, we've got s is equal to 0. We're going to plug in the 2 for the t, and I'm going to get 2v sine theta. I'll put in the explicit negative for the g, and I'm going to have negative 2g. I hope you see that, because 2 squared is 4 times a half is going to be, so just 2. And the 2's are going to cancel out as well, aren't they? And what are we going to end up with here? I'm going to say that I've got sine theta is equal to g over v. And then over here, I'm going to say that cos theta is equal to r over v. Okay, and just before we go, I just caught myself. I made a mistake. The range here, this is only a velocity. I have to multiply by the time, which is a 2. So there's going to be a 2 there. So it's r over 2v.
I must have put a decimal point in the wrong place or something. I always do that. I always mess up some mundane detail. Oh! Well, this is not a mundane detail, Michael!
I'm going to do sine theta over cos theta, so g over v. Over r over 2v. So when we rearrange this all, I'll have g over v times 2v over r. Oh, that's convenient. I don't have to worry about what the initial velocity was. Seems to be independent of that. And since we know r to be 50, it looks to me we got 9.81 g over 25. And see, this is why you wait until the end to do all of your substitutions, because things will cancel out for you quite nicely from time to time. I get that to be 0.3924, and if you do the inverse tan or arctan of that, then what you get is 21.4 degrees. How did you do?
Okay, this is from the WJEC. It's the Unit 4. It's from 2018, and we've got a question about escape velocity here. Explain how this equation is an application of the conservation of energy. For 3 marks. Okay, well, we can explain that we've got the kinetic energy and the gravitational potential energy. Okay, and the total equals 0. Now you can interpret this several ways. I suppose you could say, hey, the sum of them equals 0, and that means their total must also equal 0. Now, if the total equals 0, when you rearrange this, what you're saying is that, hey, whatever change in kinetic energy there is must be, say a gain in kinetic energy, and I'm going to explicitly put the negative here. It means it's a drop in gravitational potential energy. That's if something falls. We have a drop in potential energy and a gain in kinetic. But as we actually move outward for escape velocity, okay, we are going to be gaining gravitational potential and losing kinetic once you get up to a certain height. Now, in order for you to escape velocity, you're going to get as far away as you can. We know that the R needs to be infinite, and so the final potential energy will be 0. And then what's going to happen? All of that energy is going to be changed into kinetic energy. Okay? Something along these lines. We'll see what they're looking for here. Kinetic energy and gravitational potentially, so you refer to them, you get a mark. They are the total initial energy. Okay, so they're doing what I was kind of saying, but the other way we could talk about it would be, this is the left side is the initial, and then the final is the 0. That's kind of where they're going for here, aren't they? Final and initial are 0, and they must be equal. We have a conservation. We've not changed the total. Okay? Part 2, calculate the escape velocity. You just plug these numbers in, and I'll, just in the interest of time, I'll show you. The little m's, they'll cancel out. We don't need that. You can put an m of 1 if you like, and you get about 618. Try that for yourself.
Hey, Copernicus.
Okay, this question is from the Component 2 Eduqas. It's a part of the WJEC, but it's the Eduqas version. This was from 2017. And this is about Kepler's laws from the looks of it. They're going to ask you to describe how this diagram can explain Kepler's second law. Kepler's second law, this is, I'm going to guess, it's going to tell us that these are equal time intervals are going to sweep out equal areas. If you were to calculate the area of this tiny little sliver and this sector here and this piece here, those areas are all the same, okay? Equal areas are swept out in equal time intervals. And this happens, well, yes, as the radius decreases here, it's traveling faster, so it's going to cover more of an area. Out here, it's a very long radius, but it travels very slowly because it's further away. I'd say something to that effect for 3 marks. Okay, and on the same paper, we've got a question here on gravitational potentials. So, explain why potentials have negative signs. Well, if you remember, we had defined our potential to be 0 when we're at an infinite distance away. Okay? And you have to actually do work against the gravitational pull, which is an inward force. You have to do work against gravity to get up to 0. So that means you must be in a negative position if you're adding energy to get to 0 energy. Okay? You're an energy well, is what they're called. Another way to look at it would be if I'm moving from infinity and I start at 0, and I'm actually lowering my amount of energy because I'm working with gravity, I'm going to move into a negative amount, aren't I? Okay, spacecraft mass of 300 kilograms orbits the moon. Determine, showing your reasoning, changes the gravitational potential energy when it moves. Okay, well, let's see. So from A to B, no change in gravitational potential energy because the R is unchanged, okay? R is constant, no change in gravitational potential energy. Okay, what's going to happen when we move from B to C? Okay, well, we just said before that these potentials have negative signs. So we're actually going to be lowering our potential energy. It's going to become more negative, but we can just say it's going to be a decrease. If you want, you can say it's more negative. Okay, this one here, we said it was constant. Spacecraft is now directed from D towards the moon's surface. Calculate the speed at which this spacecraft impacts the moon's surface. Okay, so this was the potential at D. This is the potential I've got here at the surface of the moon. I've put the radius in here, the mass, and this is what I've got here. This is of course megajoules per kilogram. Okay, So what's the difference between these two? What's the change? What's our potential difference? Our gravitational potential difference? Negative 0.6275 megajoules. The work, which is the change in energy, is going to be mass times that change in potential. Okay? Okay? And look at the units. This is energy per unit mass. So if I multiply by the mass, okay, then we will figure out what energy has been changed. That's our kinetic energy then. What is the mass? What's the mass of this satellite, the spacecraft? We don't know. But we do know that it will be the half mv squared. It had no kinetic energy before, at least vertically. So those masses will cancel out for us. So we'll put that in there. We'll double it. Then we'll take the square root, and I get 1.12 times 10 to the 3 meters per second. So about 1,100 kilometers per second. So that seems to be correct. That's fine. You can do it one of two ways. I think this is the way I did it. Okay, I said, hey, that's equal to the change in the gravitational potential energy, which you get by multiplying the potential times the mass. You could just flat out calculate the energy values, find the difference, and then set equal to half mv squared. You could do it that way too. That's fine. Okay. Going back up to the beginning, we said the potential was 0 at infinity, and this is important. Underlined, you need to say work done on the object to get to infinity. Therefore, you need to be starting a negative, something like that. We said, okay, or the other way I said, going from 0 down means it needs to be negative. We had said 0 change, no change of potential, because we had not changed the r. Now, I didn't realize they wanted us to calculate things. Yeah, determine showing your reasoning. I guess when it says showing your reasoning, they're expecting you to do a calculation. All that's not very explicit.
That's all it is. You do the math. You solve one problem.
We were correct. It was a decrease, but you do need to show it. Okay, this is a WJEC PH4 paper from 2016. The mass of the moon they give. Here's the radius. Calculate the gravitational field strength. Okay, in the interest of time, I'll let you plug in all the numbers, but that's the formula, of course, you know you're going to use. Okay, moving on. The mass m is fired vertically from the surface of the moon. Show the greatest height above the surface reached is 51 kilometers. Use your conservation of energy. Okay, well, since it's equal to 0, you know energy initial is equal to energy final. I often get my students to write that out so they think about what they're doing. Okay, now what you might do, if this was a GCSE question, you would do something along these lines, wouldn't you? Yeah, you'd have an H1, you'd have an H2. What's the final height? And you'll have a delta H, and you know you'll see from whatever kinetic energy you have that'll be enough to give you the delta H and that sort of thing. Okay. Now, what you might do in that case is you might say, well, I'm on the surface of the Earth, so H1 is equal to 0, and so I'm really only worried about the change and what's the maximum height going to be. Okay. A couple of things going on here. We are not at 0 for the reference point here. What we will be doing is starting at the radius as being that height. But we're not going to use height. We're not going to use MGH, okay, because this is a little more complicated. We know that G is not constant. We know that it's inversely proportional to R. So what we are going to do is we're going to use, as they've said here for the potential, you know that the potential is energy per unit mass. So if you want the gravitational potential energy, you'll take that mass, okay, times that potential. So that's a negative G big M over R. And I can call that R1 if I like. And I'll make this a negative mg m over R2. Okay, so we can do that. First of all, let's cancel out the m's here. We know we don't need them. Okay, now I know what some people might do is they might plug in the numbers and get going on all with the calculating. And I mean, that's fine, but what I think makes maybe a little more sense is to say, let's bring over this R2. This will become a plus, okay? Or if you want, you can say it's like subtracting a negative. That's fine, okay? What would you prefer? Would you prefer to take a negative out Or would you rather just write it therefore as GM over R1 plus GM over, we're going to switch that too. So minus GM over R2. And you could do that. And if you want, you can take out GM, and you'll have 1 over R1 minus 1 over R2. Okay? And that should be equal to your half V squared. Okay? And you could say, hey, I've got V squared over 2 GM. That's going to be, and what are our radii? What are we going to have? Okay, well, 1 is the radius of the moon. And we could put in this plus some value. I think we'll just put, let's put an H there. I've run out of room. This is why it's important to be nice and neat and tidy so you don't run out of room. Let's solve it all. We'll get the reciprocal, and then we're good, yeah? So if we plug these numbers in, and that's giving me, yeah, and don't be alarmed, you've got a small number, but you're going to get a reciprocal. I'm going to carry a few decimal places. Okay, that means H is going to be the inverse of that. 1.7909, let's say, times 10 to the 6 meters. And then, of course, we need to subtract. Okay, so I've called it H, but, whatever you want to call it. So now we'll call this H max or whatever. It's going to be the radius minus that height there, yeah? And so I'll just keep on my calculator that number minus the 1.74 times 10 to the 6. 50.9 meters. Now, I've seen in some exam boards when they say show that it's 51, they don't want you to round it right away. They want you to show the unrounded and say, yeah, therefore it's 51 kilometers. Okay?
Okay.
Okay? Let's take a look at the mark scheme and see how they've gone about and done it. Okay, so up above you've subbed in those bits and you get the gravitational field strength for the moon. Yeah, so we've equated total energy at the surface. They've done a before, they've done an after. Then they're equating them. I've done that from the start, haven't I? You do some rearranging. Now they've actually done it separately. They've plugged in the numbers. They plugged in the numbers, and then you rearrange and you get your R. Okay. I don't know if I like these methods because you're writing out all these numbers. You're writing out all that stuff again and again. I do one calculation here, write that number down. I do one calculation here, I write that number down, and then I'm putting it in. Whereas here you can see we do the algebra, we do some rearranging, and we do calculation one time. Okay, I think it's more effective, less chance for you punching wrong calculator buttons. If you're in a hurry, you only have to do it one time. Punching buttons in a calculator can be time consuming. Okay?
That's just a straight shooter with upper management written all over him.
And there we go. So I think we're fine. Anyway, in many applications, an approximate value for height can be reached by the object by neglecting gravitational field strength varying with height. The variation of gravitational field strength with height determine the value for the height. Well, that's kind of what I was saying at the beginning. We would have just said, this is starting from 0, and so we'll just say, hey, we are saying here that the change in the kinetic energy is equal to the change in GPE, aren't we? Okay, and so again, the mass doesn't matter, and it's going to be v squared over 2 little g. And let's see what value we get for that now. We're going to have 400 squared divided by 2 divided by, we had calculated before, in this answer we saw was 1.62. So I get 49,382 meters. So that's roughly 49 kilometers. Yeah, okay, I had 49.38, yeah, so 49.4, yeah, right, yeah, that's what I had, so you do some rounding.
Okay, next question is on the same paper, and we're going to ignore Part A, where that's beyond the scope of this video, but we will take a look at Part B here. they want you to sketch some curves between 0.5 and 2 from the center, and the first graph is electric field strength, and the other one is electric potential, and those are versus distance. Okay, now because they've already given all of these dots, you've only got to calculate the two. So I did values of R equals 1 and 1.5. So I calculated the electric field strength and the electric potential and plotted those points in there. And this is how the graphs look. And that's what we would expect. I would like to point out that the electric field strength is the potential gradient, and I'm wondering if you took the gradient of this graph, which would be the potential gradient, if the value of that gradient would not actually be, compared to R, wouldn't that be that value? I'm wondering what's the gradient, would you say, here at this point, 0.520? I'd say that the value of that gradient is 20 divided by 0.5, so that might be 40, which is what we get here. I mean, a more rigorous calculation, draw yourself a gradient line on a full graph and do the calculation, but I think you would expect to see that. Okay, if we were to go along here, what does this look like to you? Is this about maybe a 7? 7 divided by 1.5? Well, 4.666, and look at this point in here is just below 5, so 4.666. So I think you can see that relationship there. I encourage you to explore that a little further.
I'm a quick learner.
Moving on here, we've got a second identical sphere added on, just like the one we had before. That's the charge. It's brought from a distance to a point that is 1.5 meters from the first sphere. Determine the work required to do this. The work required to do this is the change in potential energy. That's charge times the electric potential. And this is similar to these gravitational potential questions we've had. And so, you would have, instead of G m little m, we've got G q squared, because both these charges are the same. It's not a matter of a one large charge and small charge like we do with the masses. You've seen this bit before. You know how that works. We plug it all in, and then we got our answer there. Okay. Determine the magnitude of the electric field strength at the point between the two spheres. That is 0.7 from the left-hand side sphere. Show the direction of the field at this point. Okay, so we want to find out the electric field strength. This is 1.2, so 0.7's over here. So if we've got a positive chest charge, which is in this area here, I would say we're going to have less of a force pushing on it and more of a force from this side. We would expect the electric field strength to be to the left, I would imagine.
To the left, to the left.
Right, so the thing I want to say about this question is that this electric field strength at that point, it's the net force divided by the charge. We know that this force is going to be larger going to the left because it's closer than the force coming from the right there. Now, I think because I want the net force, I know I need the force coming from the right. We know that's going to the left, but that is the larger of the forces. In the end, it won't really matter what you do, but we do have sign conventions to talk about. So I'll do the larger one first. Okay, that is the one going to the left.
To the left, to the left.
Okay, so if by my sign convention I want to say to the left is positive, that's the larger one. I would put that one first. If I want to say to the right's positive, I'm going to say it's going this way and then subtract. We can keep the left right in there. That's fine. We know that the left, because it's all going to come out in terms of the direction, right? So we know that the left distance is 0.7. So it's 1 over 0.7 squared minus 1 over 0.5 squared. Now, when I do that, I get a negative value, as I would have expected. I get negative 1.9, let's say 6, times 10 to the 4. Okay, and that is newtons per charge. Had we plugged in the larger side, saying to the left was positive, we would have had 0.5 minus this. This would not have been positive, but we would have said in our convention that it was to the left. Okay, so I've just used normal conventions, and that's why my negative says to the left. If you want, you can say it's 1.96 times 10 to the 4 newtons per coulomb to the left.
To the left, to the left.
So we'll check out our answers. Those are the same values that I had. Of course, they've got times 10 to the 3 here. I had it multiplied out, but that all works into the graph, into the table. So for 3 marks, point or implied from the curve for the approximate E, approximate V. Shape of both curves with decreasing magnitudes at increasing distance, fine, and E decreases faster with distance, and both curves passing through 10. So I mean that's what we had. They both travel through the point, the 1, 10, and this is a steeper curve and it's going faster. Yeah, definitely. Okay. All right, moving on. That's the value that we got. That's the work. Okay, that's your definition of the electron volt. Remember. Okay. I didn't quite go in with this calculation, but I think I didn't explicitly state it. I'll explain it now, right? So the final radius is this 1 point. Why do I have 1.5 there? This final distance, it's 1.2. That should have been a 1.2. And the initial distance was infinitely far away. And if it's infinitely far away, this goes to infinity. This whole term goes to 0. So it's really just this term, isn't it? So that's what I've done on here, yeah. Okay. And the final one, we had plugged it in. We've already discussed the theory behind all this stuff. Don't forget your units. You get a unit mark. You get a unit mark. You need that unit for the mark. Okay. Direction to the left except negative sign or arrow. Yeah. Okay. So again, we just got to justify the direction. That's what we did. I've done left minus right. We know the force to the left is going in the positive direction, so it makes sense to have that one first, and then you subtract the one going to the right. But you can do whatever convention you like. Okay. And let's see. Electric field strength. Now I've said newtons per coulomb. They've said volts per meter. Can we agree that these are the same units?
It can be done.
Well, it's like this. A joule is a newton meter, so a newton would be a joule per meter. And what's going on? I've got a charge underneath. Oh, and then we've got that other equation where we said that energy was equal to charge times voltage. So that means that voltage is equal to energy over charge, which is what I see here, and that's why we got a voltage volt per meter. So yes, the units either way work out.
No. Are you sure?
No.
Of course I'm sure. With physics, I'm always sure, yes.
Okay, and on the same paper, we've got a star and a companion planet, mutual orbit, about a common center of mass. We've seen this, okay? They give you an orbital speed and the period. Right, so this is a Kepler's law, isn't it? I get here 4.987 times 10 to the 29. Of course, we need to do the cubed root. Please make sure you are doing the cubed root. I know students might be inclined to put the wrong exponent there out of force of habit. Okay, and I get 7.93 times 10 to the 9 meters. 7.93 times 10 to the 9. Right, so it's a 5 marker. 1 mark for changing your time into seconds. 1 mark for talking about the approximation. Okay. Did I get that mark? Did I get that mark? I only wrote this bit in the formula here. You might be wise to say, hey, it's this, but I know that's going to 0. You could just do that, and I think you get that mark. I think you need to make a note of that. All right? Be wary, please. Okay, and then, yeah, rearrange, substitute, get your answer. Good. We found the distance between the star and the planet. Now they want to know between the star and the center of mass of the system. Now remember that up here, the star has an orbital speed of 56 meters per second. So we do have that speed there. I think we can just rearrange this equation, can't we? Right? Velocity times period, that'll be a unit of distance, and then divided by 2 pi will give us our distance. Right, so I get 3.26 times 10 to the 6 meters. Use your answers in part B and C to determine the mass of the planet. Okay, and here we go. This formula is the specialty for WJEC. I don't see other exam boards doing it. Remember that little m will be the mass of the planet here. Big M is the mass of the sun. This is the equation you will have seen. And so we're not going to ignore the mass of the planet underneath now. So we're going to want to rearrange this for little m, aren't we? Okay, so we'll have mr, little mr equals md. We'll get big MR is going to be md minus r. So the mass of that planet is going to be the mass of the sun times r, which we've just calculated, is that little distance between the sun and the center of mass, and then we're going to divide by this distance of the difference of this distance between the actual star and the planet minus that little distance there. And if you think about this system of what we're talking about, here's the center of mass. This whole thing here is d, and this little bit here is r. So we're dividing by, this difference here, because it's a ratio of mass to distances, isn't it? Okay. You might think, hey, that's insignificant, but perhaps not. I get 9.08 times 10 to the 26 kilograms. How are we looking here? That's what we've got. Well, okay, they've got 9.09. Close enough. Good. Right? So it's the same thing. And you'll see they've done the algebra, they've done the rearrange. I think you would agree, plugging in the numbers and rearranging every step of the way. Okay, so now I have to multiply this number through. Now I have to subtract it. You're grabbing your calculator every single time. I can't stress this enough. Do the rearrangement. Become better with your algebra. Plug the numbers in one time and get your answer. Does it make sense? Yeah, okay. It does need to be smaller than the mass of the sun, and it is. Okay, and did we... Yeah, we already checked that one, didn't we? Yeah, well, we were right about it, and we used it down here. You do get error carry forward if you're wrong, so that's fine.
Okay, and this is an OCR, paper 1 of the Physics A. This is the modeling physics one. Write an expression for the gravitational potential. We know it's this. Okay, and show that the escape velocity will be given by this equation. Remember, we've done this a few times now. The kinetic energy plus the gravitational potential energy, so the gm over r times the little m, is going to be equal to 0 at the end. It's about paying off the energy debt. What kinetic energy is required to replenish this negative energy that has been established as an energy well? And if you rearrange, you get that expression. That's fine. Okay. Calculate the escape velocity of the gas molecules on the surface of Pluto. You're just going to plug in these values to that equation, and you'll get it. That's fine. Plug it in. Okay. Explain why Mercury has no atmosphere while Pluto still has a thin atmosphere. Use data from the table. Okay, so 3 marks. Well, what do we want to say? If you look at the table here, and you could actually calculate the escape velocity for each of them. Okay, if you look here, I would say that Mercury's mass is probably it's at least 10 times greater, and I would say if you doubled the 1.3, you'd get 2.6. So I mean, it's well over 2. But we'll just say it's that therefore altogether 20 times greater the mass. And so if it's 20 times greater, then that means the square root of 20, your velocity would be the square root of 20 times greater. But the radius, I would say the radius here is also a little over double. Okay, I don't know if it's 2.5. I wouldn't say it's 2.5, but it is well over 2. Okay, now that means if you've got a larger radius, you're going to be 2 times smaller. Okay, so we've got 20 times larger over the 2 times smaller, so we end up being only 10 times larger. I would expect a root 10 in these differences. Maybe if you do those calculations, maybe that's something you could talk about. You would see the difference. What is the real big deal? The big deal is that Mercury here and Pluto, we see Pluto is about 100 times further away. Okay, so it's not so much about what is the escape velocity of the planet Mercury or Pluto, but also how much energy. Okay, Mercury here is the hottest or second hottest planet in the solar system. The particles on the surface will have a very high energy. very high kinetic energy, and most of them will have a, if you want to get into your thermodynamic stuff, they'll have, because you know there's a distribution of the temperatures. We can talk more about that in the thermo video, but you're going to have root mean square value. Most of those molecules on Mercury will have the escape velocity for Mercury, okay? Whereas with Pluto, you know, it's still got a thin atmosphere. It's pretty cold out there, and as a result, I would say not enough particles are going to have the energy, the escape velocity, which is, you know, they're not going to have, a lot of particles won't have the energy because of the temperature, which would translate to, you know, by the distribution of your speeds. If this is what you need for escape velocity, only a few amount of them will. Okay, many of these other ones will be below that threshold speed, and so that's why there's some particles left behind. Let's see what they say. Right, so that was our expression. Right, so that was our expression. That's good. You can add these together and then you rearrange. We've done that. There's your escape velocity for Pluto. Okay, plug it in. There's your escape velocity for Pluto. I believe my calculations from before, it was much higher. It was not quite root 10, but a little larger for Mercury. But so you can, what we were talking, oh yeah, here it is. Yeah, here it is. So it's about 4.2. Okay, if you wanted to, you could calculate the escape velocity for Mercury, say it's got a higher escape velocity. Okay. Or other way around, you could say Mercury is closer to the sun and therefore Mercury is hotter. You can't just say Mercury is hotter because it could be from other factors. You have to say it's hotter due to it being closer to the sun. And if it's hotter, even though it's got a higher escape velocity, they're going to have a higher kinetic energy. Okay, molecules on Mercury are more likely to have higher speed than the escape velocity. Okay, and words to that effect the other way around. Pluto, as I was saying, will not have the escape velocity. These particles will not likely ever reach that. Okay, you could say required speed for escape velocity. You could say fast enough to escape. That's fine, but you know, try to be technical. Use your terminology. Okay. Okay, and this is a great question on gravitational and electric potential. This is from the Cambridge Pre-U June 2012, paper 3. So we've got a map here with the contour lines shown here. Okay, you understand from your geography class that each of these points on the line represents equal height. Okay, and the lines are drawn at intervals of 200 meters. Now, calculate the change in gravitational potential between points A and B on the map. Well, it's going to be what we had just done, divided by the mass. Or you could just say, hey, I know potential is G times delta H. Okay, remember that potential is energy per unit mass. So mgh divided by m is just gh, but because it's the change in height, it's the change in potential. So it's G delta H. Either way, 39,024 joules per kilogram. On figure 3.1, draw 6 lines with arrows to show the direction that water could flow from the top of the island to the sea. So we'll draw a line which is perpendicular to this, and then we would need it to be perpendicular to each of these lines. So I would say I'll draw a line like this. All right, and state why the gravitational field is not in the direction of the 6 lines you have drawn. Well, because this is a top-down view. We are looking down in the direction that the gravitational field is acting. Okay, these things are, we're just looking at the top-down view of which way the water would go. Those lows are not field lines. Okay, the gravitational field lines are acting down. We see the equipotential, and we're just trying to map out where the water would go. That's what's going on there. And then here, same diagram, except they've changed it from meters to volts. Okay, now it's electric potentials. Okay, it's an object surrounded by a conductor at 0 potential. All right, so it's got a potential inside. Draw 6 electric field lines on the object. That's the same thing, isn't it? Right, so something like that. Look at, I went right through D, didn't even mean to. Calculate the work done when a charge of 50 microcoulombs is moved. Remember that energy is equal to charge times voltage. Okay, so just plug in those values, and it actually, if you'll notice, from A to B is going up 400 volts, C to D we are going down, and there's a negative there. So it's the same answer each time, 0.02 negative for the C to D because it's a decrease in electric potential. We've done that calculation there. You could, yeah, so I've chosen joules per kilogram. They've done it this way. They've done G times delta H, but like I say, you take that and divide by the 50, you should get same thing. And again, they've rounded 3 sig figs, haven't they? Attempt to make the lines cross contour lines at right angle. Yep. Subtract 1 for every 2 glaring discrepancies of this. And that's it. That's all. You just draw your 6 lines, and as long as everything's right angles, you're fine. Okay. The gravitational fields into the page, we said. Good. Same thing. Attempt to make the lines cross. Equipotentials at right angles. Arrows in the right direction. What is the right direction? It's got me wondering here. We're going from high potential to low potential, I suppose. And I wonder if the water example from up above is a way to be an analogy for us to remember which way these arrows go. We know that electric fields go from positive to negative, but this is a potential. Positively charged. There we go. So it's going outward, yeah? Might have been helpful to make sure I read that in the first place. Okay, this is a Cambridge Pre-U paper 3 from 2017. This is a graph of gravitational field strength, okay, G plotted against the center of the Earth. Okay, so we can see here that from 0, from the very center of the Earth, up till about a little over 6,000, okay, that's the radius of the Earth. It's increasing at a constant rate. It's directly proportional to the distance, and we get up almost to 10, so that's our 9.8. And then as you get further away, it drops off. Okay, so use this data on the graph to determine the radius of the Earth. What would you say here? So this is 6,000, and so this is going to be 400, 800, 720. That's the halfway mark. That'd be 6,200. So we're a little bit over 3. So we say 6,350. I would say the radius of the Earth is 6,350 kilometers. Get that from the graph. Okay, and then also from the graph, determine the gravitational force on a man-made satellite with a mass of 20,000 at a distance of 8,200 kilometers. Okay. All right, so again, if I zoom in, each of these, let's see. So this is going to be 10,000. Each of this will be 8,400. So the halfway point here is 8,200. So 82, see, right at where it crosses the 6th line, I think it's a little bit over 82. I think we want to be in this area right about there. And given that this is going to be 6.2, and we are, I'd say what would you say? A third of the way? If I get my dot out of the way, if you kind of see here, I'd say it's a third of a way up. So I'll say 6.03. Well, 6.33. Oh, no, because it's a third of, to get to 0.2 here. I'm getting a 6.066 repeated for the G. Gravitational force is the weight, so it's just going to be that G, that times the 20,000. So I get 121,333.3 repeated. Can we just say 121,300 newtons? Calculate the speed of the satellite. Yeah, well, we can rearrange your centripetal force, MVR, and because the weight is a centripetal force, and you can solve for V, but that's beyond the scope of this video. What is meant by the gravitational potential? Okay, we've seen it several times. Let's get it straight. It's the energy needed per unit mass to move an object from infinity to a specific location, distance from somewhere else, distance from another object. Use the figure to estimate the gravitational potential at a distance of 10,000 kilometers from the center of the Earth. Well, that's 10,000. Seems to cross exactly at that point. We'll just scroll along. I get 4 gravitational potential. So my G, I get 4. Right? Gravitational potential is negative gm over r. We saw up above G is gm over r squared. If we want to rearrange for gm to be gr squared, what we can do is we can do that. So that'll be gr squared over r. So it's negative gr. That might be a new one. And we've measured the 4, and we got the 10,000. So I would say 40,000 joules per kilogram. Right? And it's actually not 40,000 because this was kilometers. So it's actually 1.0 times 10 to the 7 meters. So if I add that on there, I actually get 4.0 times 10 to the 7, don't I? Okay, let's check our answers. This is very confusing. It's not 1.63 or anything like that. This is for part 1. This is for part 2. They could have used a couple spaces. I think the value we read was within this 6,300 plus or minus 100 kilometers. That's fine. Okay, 6.1. Again, we had 6.0666, so plus or minus 0.1. So again, we're within that parameters. Okay, or yeah, 20,000 times that. Yeah, and so you get your answer. And that's what we had, all right? 122,000 plus or minus 2,000. So again, we were within parameters. That's great. I'd like to think we were really good on that one. Zooming in helps. I'm not sure what you do on your exam. I hope you've got good eyesight. Okay. Right. BII, you just plug in your stuff and you get an answer. No big deal. Right. We skipped this. Not in our thing. Gravitational potential energy of a body per unit mass. Okay. So it's only one marker. So what is meant by gravitational potential? Yeah, for 1 mark, you can say it's the energy per unit mass. Fine. Okay. We also know it's the energy needed to bring an object from infinity up to another point. But in this case, they are saying it's the energy per unit mass. Okay. I suppose the more advanced definition comes with a higher mark count. Okay, and we had our potential. We subbed in, we got GR in the end, didn't we? And it all worked out. That's what we got. Oh, should it be negative? Yeah, it should be negative, shouldn't it? Okay. It doesn't look to me like they penalize for not having that. Okay. Another way you could be marked for this is, do you recognize it's the area under the graph from the point to infinity? Oh, interesting. Counting the squares. Okay, around 200 or more for some large distance, converting the value of the square, and you get the total gravitational potential energy. Oh, outstanding. Okay, so the area under the graph from the point to infinity. Okay, so we could have drawn that line here, and it's the area under the graph here. Interesting. So let's see, gravitational field strength is this, from what we had seen before, times a certain distance r. This would cancel these things out. And what is that now? That's no longer g. That's your potential.
Check out the big brain on Brad. That's right.
That's what we just saw in the mark scheme there. We had plugged in the GM. You remember what we had done. But you see, it would be this times the r. So area under the graph, because it's g times this distance, r.
That's it. I think so. You. No. No. You're very good, you. No. You are very good,
There's a lot more to it than that.
You're very good, you.
There are underlying things
You understand me? No, you're right. You're right on the money.
So interesting. You could have done the area under the graph, all of these, all the way to infinity. Well, there you have it. Okay, and that takes us up to the end. I hope there was some useful information, some little hints and tidbits there that will make your future exam work more fruitful. Thank you, and we'll see you next time.